clue what it means, but you read the data sheet and you make sure you program it accordingly. It's very much EEPROM specific or hardware specific. So there are certain reasons for this, but I have no clue what these exactly mean. But it is explained what you need to do. So you just make that happen. You can write a new address if you want to, new data if you need to. We talked already about that. Then you write a logical one to the EEMPE bit while writing a 0 to the EEPE in that EECR, that control register. And you have to do that at the same time. So let's go back. So we have this one, and I think it was that one. We don't know. I now forgot. And the 0 to the EEPE, which is this particular bit, of course, because you say you're ready, you're done, you have finished the writing or reading to EEPROM. Within 4 clock cycles, after setting the EEMPE, you need to write a logical one to EEPE. So this is the structure that you do. So that's just defined as such in the datasheet. That's the spec. That's how you operate it. Now 4 clock cycles means really the next instruction, because it takes 4 clock cycles to execute an instruction. Because you will fetch register values, then you manipulate those, and then you write it back. And that's why it takes 4 clock cycles to really finish up one instruction. Okay, so then you write a logical one, and then at some point this is reset back to 0 once the actual reading or writing is finished, and the EEDR register is either populated with the value that you want to read from this address, or the value at this address in EEPROM is written with what you had in that register. Okay, so let me have a look here. So here's an interesting cautionary note. Yeah, let's have a look at it too. So an interrupt between steps 5 and 6, here we are, will violate this within 4 clock cycles, right? And that will make the write cycle fail, and that is of course bad. So what you want really is that an interrupt routine accessing EEPROM if that is interrupted by another EEPROM access, then these registers will then be modified accordingly and so forth, and everything gets into a mess. That's effectively what this tries to explain. So it is recommended to have the global interrupt flag cleared during all the steps to avoid these problems. So what we often see, also in the macros that you will call, that are written by Admel, right? These Admega libraries, you will see that when you execute this, you will wrap it in a wrapper where you first disable the global interrupts, and then after that you enable it again. Now, alright, so we have more bits in that particular control register. This is the EEPROM read enable. We talked about a write enable, so it's something similar. Then we have, if you look at the data sheet, you see a code like this. It always comes in 2 kinds. One is assembly code, and one is C code. So here we see that we do exactly what was stated in the specification. We wait for the completion of the previous write, so you wait till this particular position has a 0. Then you set up the address and the data, which are the input to your function here. Then you need to write this logical one, and 4 clock cycles later you need to have done this. So, well, this takes 4 clock cycles, so the next instruction must be this particular construct where you write a 1 to the EEP field. This is just what you need to do. Now, this particular code does not exclude the possibility of an interrupt right here in the middle. So, in order to avoid that, it's a very unlikely chance, I must honestly admit, that would happen. but it could. So if you want to write safe code for some application, you may want to wrap this around with a disable of global interrupts and an enable of global interrupts right after. But if you do that, then you may miss out on some interrupts that should have occurred or should have been queued up. So anyway, these are the decisions as an engineer that you will have to make yourself, depending on the application that you're working for. So here we have the read. It's the exact same piece of code, but instead of setting up also the data register, essentially now return what was in the data register, because that's what you read from that particular address over here. Have a quick look also at the assembly code. So you see these types of instructions. So if you're interested, you can have a look what all of this truly means. So these operations, you see registers, R18, R17, and so forth. And some, here you've seen input, so R16 gets into gets into the EEDR, and so forth. And then we have a return instruction as well. So it's kind of interesting to see how this reflects what we do over here as well. Alright, so now we talk about an example code. An example code here, we do something somewhat straightforward. What we first of all want to make sure to do is to include the EEPROM library, because that has those macros that we're just talking about, these kinds of functionalities that we are going to use. And we're going to do something in the following way. We're going to define EEPROM true and EEPROM data as two addresses. Don't think those as being values. We have a whole range of memory, EEPROM memory, that is addressed, and we're just interested in the very first two addresses, labeled 0 and 1. What are we going to do? We are going to store something in EEPROM, and we want to somehow find out whether we have used the EEPROM for storing data address 1, and that is being stored in this particular value. So at default, the whole EEPROM is all 0. So what we can do is, if I have already stored some 8-bit value over here, for example the letter T, the character T, then I say, oh, I already have a value stored in my EEPROM. And then I can use the EEPROM read byte instruction. I think that was, this is being used in another function that we have over here. So we have the EEPROM read byte. So you read that particular one, and that gets pushed into this particular variable. Now have a look at this instruction here, by the way. It looks a little bit weird. This particular functionality needs to know what address to look at. And if you write a star here, then even though this is simply a global value, this is simply this particular EEPROM data, which after the pre-compilation is changed into a 1, then this particular star here will interpret this as an address, and then it looks at the value that is stored at that address. And that's what this particular guy does. That's what this means, right? So you want to explain to the compiler that the variable that you have is a pointer. That's what that star means. That points at an 8-bit integer value. So that's what this particular construct means. So do a typecast, because after all it's just translated into a 1, and that is considered to be an integer, but you want to typecast that as that 1 interprets a pointer, or equivalently an address at which a value is being stored of this particular type. Alright. So what we're going to do then is we're going to read from that address, and we're figuring out its value, which we call, say, time. So we store some data over here at this address 1 that we call time in our program, and you read it from it. If you have not yet stored anything over in the EEPROM, then we would not have this particular condition to be true. Because if we read from this particular address 0, then the value that we read is initially default to the 0 character, and 0 is not equal to the true, to the T character, the 8-bit T representation. So else, if that happens, we will set time to 0, because effectively we have not done anything so far. It's really the first time that this code is running on your MCU, and before that time it had never been reset in some sense. So, okay, so it's a type of code that you can use. So, for example, so look, we use this code snippet, and we're using a slightly different way over here. For example, suppose in this piece of program we have a button push, and if that happens, then I want to make a snapshot of some variable. For example, I want to so forget about this part for a moment. I want to write some data. Some data called time into this position that is pointed at by this address. So remember again, we have the EEPROM data is equal to 1, which is just an address in EEPROM, and the EEPROM write byte functionality will take that address 1, goes to that address in the EEPROM, and right there writes the value of time. Now, what we're going to do here is that we have this code fragment initially that then says, okay, we're actually really writing a value over here, and so let's make sure that we record that in the EEPROM true address. So now we write the capital T, the character T, and it indicates that we actually have something of that means something like a time written at EEPROM data address. Now you only do this if this is not already equal, of course, to the true character. So that's how you would go ahead. Now, in this particular case, we also write the time to the UR so that you can see what that is. So this is a piece of code that you probably will be using to experiment with EEPROM. So you actually take snapshots, and then later on you should be able to get to effectively unplug the power. You put it back on, or you do some reset operation, and you can read out the time at the moment at which you had pushed, say, the button. Alright, so now we go to, so are there any questions about this part? Before we move towards the next part, and we will be gluing what we call the watchdog, that I'm going to explain in a moment, and in that we will be using some EEPROM as well. Any questions about EEPROM? So the important thing to remember is that we work with addresses that are pointers that point at effectively a data value that is stored at that address. So an address is just a labeling, right? There's some control circuitry that translates an actual address with muxes to a specific point in your EEPROM in this particular case. And from there you then read its value, or you write a new value in that position. So you're working with pointer structures, and that means that you're going to use these types of typecasting in order to tell the compiler that what we have here is actually an address that points at such a character or some 8-bit value. So now we'll do nothing more complex with pointers than this over here in this semester. But this is sort of it's still kind of, I know, a kind of a different concept than what you may be used to. So I hope you will really internalize this and ask questions whenever those occur. Okay. So we will proceed a little bit with the watchdog time. We don't have too much time left though, but we will continue then on Wednesday. Now, what is a watchdog time? I'd like to at least give you some feeling of why I think it's actually a kind of a cool mechanism that the MCU controller has. So let's have a look at it. So what do we read here? So in interrupt mode, the watchdog timer gives an interrupt when the timer expires. So you really have a separate time. So it's timer 0, timer 1, timer 2. We even have an ADC clock, but that is sort of clocked off from the original MCU clock, but just like all the other timers, by the way, with prescalers. And you have another clock, which is this watchdog timer. So it gives an interrupt when the timer expires. And this interrupt can be used to wake the device from sleep mode. So that's interesting, because the watchdog timer keeps on being functional, even if you go into some sleep mode. And you can also use this as a general system timer to wake things up, whatever you want to do. So the watchdog timer, you've programmed, expires, say, in exactly 2 seconds. Well, that may lead to an interrupt corresponding to the watchdog timer, and with that you can do something specific. So it's another accurate clock that you can use. So one example is to limit the maximum time allowed for certain operations. It's also possible. So something takes too long, and effectively you have a watchdog, something that looks over the main program, seeing whether those executions do not take too long. Because maybe it's waiting for some peripheral, but the peripheral is broke or something like that, or the main program does not move forward in the way that you would expect. Now, in the system reset mode, the watchdog timer gives a reset when the timer expires. That's interesting. And I'm very much interested in the following type of system here, just to give you some idea. So there was, I do not exactly know when this paper was published, I forgot, but there's a famous paper called the Therac blah blah. So the Therac was a X-ray machine. So patients would go in there and they would have an X-ray taken of them, and then of course that would be analyzed by the doctors. Now, it turned out that there was a little programming bug that would occur very, very rarely, but it occurred about 8 times, in which somehow the X-ray kept on going, and those 8 patients were burned alive. They died. And that was in a period when, first of all, the X-ray strength was much more than what we now have in our, say, when you go to the dentist and so forth. But the point is, that I try to make here is that you have a machine. What you want to do is you want to create a system that is doing the logical functionality of what you want it to do, but it's very sensitive. You need to make sure it's completely safe, but you cannot be sure. We cannot trust ourselves to make those bugs. It happens, unfortunately, and even with advanced techniques, like formal verification, so forth, we can go up to a certain point right now where we can do some verification in logical methodology. So what you need to do is you need to actually also build a second system that watches over the system that you have programmed, so that other system can interrupt when something really bad could happen. So, for example, a watchdog timer can be implemented in a completely complementary way from whatever you do. So, which is that you can read from the X-ray machine, whether it's on and off, for example, and a watchdog timer, whenever you call the X-ray machine, then the watchdog time in this particular case needs to be set, when you talk about X-rays, to a very short time interval, but then you would trigger the interrupt or the system reset mode if that X-ray machine is on for too long. A totally orthogonal mechanism in a hardware module called a watchdog timer that is not controlled in a certain way by any of the other parts. So, having said that, there are a number of modes that you can do. So I like the idea of the system reset mode, so we'll be working with that. But there are other modes that you can have. So here we have another example. So for example, well, instead of temperature, you could read X-ray, right, in the example that I just explained. But let's think about temperature. If the temperature is too high, then the application should turn off. So what you could do is you could implement a watchdog timer. There are a bunch of components that you try to pull together in order to make this work. The first is, let's say you have some independent heat sensor, and it causes an ISR when the measured temperature is low enough. So the contrary to high enough, so low enough. Now, if that particular ISR is called, then it's going to reset the watchdog. It tells the watchdog the temperature is still low. Don't worry, you are programmed to shut off the system in, say, 1 second. Don't do that. You can start your counting back from the highest value, that say 4 seconds down to 0 seconds. So it resets the watchdogs, and then after that it disables the interrupt service routine. Then what you will do is that the main program is in control of regularly checking whether the temperature is low enough. So you can program it the way you want it to be. So the main program can regularly enable the ISR related to the heat sensor. And whenever you enable it, you know that when the temperature is low enough, it will actually call the ISR, it will reset the watchdog and disables itself and so forth. So the watchdog will now only turn off the system if one of two things happen. The sensor could break, meaning that no ISR will be called in a sense, right, because nothing happens. And then the watchdog is not reset, and so on. So the watchdog will at some point be resetting the whole system, and that's what you want. Something was wrong. If the temperature is too high, then also no ISR will be called, because it will only be called if it is low enough. And then also the system will be reset by the watchdog. So in this way you have some kind of a safety net. So if the sensor breaks, or if the temperature is too high, the system is going to be reset for you. And of course in software, one can always reset the system if the temperature is too high, but how do you know whether the sensor that measures the temperature is actually functioning correctly? So the idea here is that you're not relying on a sensor to tell you something is wrong, but you're relying on a sensor to always keep you updated that everything is fine. So the sensor always needs to be active. If it's not active, then clearly the sensor is not working correctly, and you need to reset the whole thing and repair that. So that's the difference. So we'll get into this next lecture, and we will go over this once more, and then we'll talk about the code related to the watchdog times. We'll do that on Wednesday. Alright, great.